Hello and welcome to part 2 of state space modeling. So, today we will be talking about linearization of state space systems. So, in part 1 we saw that there are certain benefits of moving from the transfer function to the state space domain. Primarily we are dealing with nonlinear systems, we could deal with multi-input, multi-output systems and so on. We saw that in the examples of the electric circuit where you had two sources, a voltage source and a current source, you had multiple inputs and multiple outputs. So, today what we are going to see is that practically all the systems we consider in the world for engineering are all completely nonlinear, right. And yet there is a good reason for us to not work directly with nonlinear systems. We actually would like to work with the linearized version of nonlinear systems. Okay. There are a couple of reasons for doing this. I'll explain that. So, we will see why we need the linearization procedure, and I'll explain one specific way of doing the linearization, which is by using the Taylor series and the so called Jacobian matrix. Okay. And we will end with two fun examples. Yeah. So, that is a basic structure. So, we will see what is linearity, then we will go to Taylor series and the Jacobian, and then we will conclude. Okay. Good. So, are physical systems linear or nonlinear? They are all nonlinear. There is no physical system which is completely linear. But before we even go ahead with seeing what do I mean by a physical system is nonlinear and then how to handle this, it is important for us to understand the meaning of linear or nonlinear. And the reason why I would like to stress a little bit more on this, even though you have done this in electric circuits or what is called network analysis, is because most students are not comfortable with the distinction. Okay. So, we remember it as a definition that there should be a superposition property, but it is not too clear what it actually means. So, let us see a very simple illustrative example of linear and nonlinear. Okay. So, we consider two functions. The first one is y equal to 3 times x and the second one is y equal to x square. Okay. And the question I am trying to pose is which of the above two functions is not linear, all right. So, if I just plot this particular function, let us say the x axis is of course x and then I plot the output over here y. So, if I look at y equal to 3 times x, the curve will actually be something like this. Okay. This is at the origin 0. Okay. So, when x is 0 you have y equal to 0 and then it goes linearly like this. If you look at y equal to x square, it is a function like this, all right. And now the question is which of these two is linear or which one is not linear, all right. So, the way that we have studied this in electric circuits or even in math, to answer this we actually invoke the property of superposition. Okay. I will explain superposition in a slightly different way, all right. So, let us see which of these two functions is nonlinear, and the way we are going to do this is to assume that each of these systems, each of these mathematical functions are actually systems, all right. So, let us consider the first one. We have a system with a gain of 3. Okay. There is another system which is like this. Okay. I give in inputs for both the systems. Let us in this particular case take only 2 inputs, okay, and I have an output over here. In the first case I am looking at y equal to 3 times x, all right. In the second instance I am looking at an expression y equal to x square. Right. So, this is actually a squaring system over here. In both the cases what I am assuming in this specific example is that I have an input x1, I have an input x2, in the other case also I have x1 and x2. And for the sake of simplicity, but this is not required at all, but for the sake of simplicity let us just assume that x1 is equal to x2. Okay. And we are going to assume that this y equal to 3x or y equal to x square are basically models of some physical system. Okay. And let us look at these two tables on the left over here. So, for y equal to 3x, okay, and remember that we are assuming x1 equal to x2 in both the cases. So, y equal to 3x, I take x1 and x2, and I am going to define x is equal to x 1 plus x 2. All right. So, this is the basic equation which I am going to use. So, when x is equal to x 1 plus x 2, and I consider x 1 and x 2 with these values, okay, x then becomes the sum of each of those, right. So, 1 becomes 1 plus 1 2, 2 is then 2 plus 2 4, and so on. Now, let us look at the function y equal to 3 times x. I can look at it in two separate ways. I can either look at it as y equals 3 times x 1 plus x 2, because remember x is equal to x 1 plus x 2, or I can treat it in this way, y equal to 3 x 1 plus 3 x 2. All right, and let us see if both produce an identical answer, and we see in this particular case they actually produce exactly the same answer. Okay. So, this is exactly what we mean by a linear function or a linear system, and I will explain intuitively what this means a little bit later. Okay. Now, let us look at the second function, all right, which is y equal to x square, and again there are two ways of writing this, y equal to x 1 plus x 2 whole squared. I can also assume the signals are being added in the following way, and remember x 1 and x 2 are signals which are input to my system. Okay. We all know this is high school math, that these two expressions are not equal to each other, right, and we can actually observe this over here. So, what is the interpretation of this? Okay. So, let us see what is the interpretation of this, assuming that these two are models of two different physical systems. Okay. So, what it means is as follows. So, let us take the first one, which is 3x. So, I have two inputs. It is not necessary to just have 2, I can have 10, 100, whatever you like, and this can be written in two ways, right, and we have just seen this. It is either 3 times x 1 plus x 2, or it can also be written as 3 x 1 plus 3 x 2. So, what is the interpretation of this? If x 1 and x 2 are two signals, right, as functions of time, all I am saying is that I can add up the two signals x 1 and x 2, and I can pass them into this system called 3, or I can pass each of these signals into the system 3 and add up the result later. How would that look like? That would look as follows. So, I can take x 1, I can take x 2, I can add these two up in a summation block. So, I get x 1 plus x 2 over here, and remember both are signals, and I can pass them into a block called 3, I get y. Okay. The other option is I can pass each of them into a block called 3, which is the model of the system, okay, and I can add them up over here in order to get y, and both these systems are exactly the same. And if this is the case, this is actually what we mean by superposition, actually a part of superposition, not the full thing, but this is what we mean by superposition. I can pass my signals through the model first and then look at the output, or I can pass each of the signals through the model and sum up the response afterwards, and you are going to get exactly the same answer. And we have seen this in linear electric circuits, where we apply the principle of superposition to actually compute system response to different sources. Okay. What happens if it is nonlinear? Well, if it is nonlinear, we have just, so we take the two signals again, x 1, x 2, and we pass, okay, so we add them up. Okay, let's, okay, so we take two signals x 1, x 2, add them up, you get x 1 plus x 2, and then you pass it through this block called the squaring block, and you get your y. All right. Now, this is not equal to taking each signal, squaring it up, okay, squaring it up, and then adding them. This y over here is not equal to this y, and this basically violates the principle of superposition. Okay, so it violates the principle of superposition, and we can see that in the first case y is nothing but x1 plus x2 whole square, and the second case what is it? It is x1 square plus x2 square, and these two are not the same. There is a factor, a residual factor of 2 x1 x2 which is left out, right. So, again, if you violate superposition, it essentially means that I cannot mix my signals, pass it through the system and say that it is the same as passing each signal through the system individually and then mixing it up. Okay, that is not true for a nonlinear system. So, good. Now we know what is linear, what is nonlinear. In a general sense, we have understood superposition. This applies to all physical examples, electrical, mechanical, and so on. Examples of nonlinear systems, I have just put 3 over here. There are thousands of examples of nonlinear systems. So, there are your diode behavior, it is actually one of the classic examples. So, you have this kind of a response over here, right. So, in this region it is linear, in this region it is absolutely not, it changes completely, right. Even if you look at a nonlinear mechanical spring, and there is no such thing as a linear mechanical spring, all springs in life are really nonlinear. Okay. So, if you look at the nonlinear spring, again you have this kind of an effect, right. So, all these are nonlinear examples, and there are thousands of such. So, while the claim is that all systems are actually nonlinear, what happens in practice, many times we see systems which behave as if they are almost linear if we ignore certain very small effects. So, for example, I can have a spring which is like this, okay, which looks almost linear everywhere, okay, and my range of operation of this particular spring, depending on the application I am looking at, maybe it is only in this range, right, and I do not need to worry about what happens over here or over here, because my operation actually happens in this particular range. In this case, it is enough for me to just use a linear model, right, and I do not need to worry about the nonlinear effects, and this is actually what happens in practical engineering. As far as possible, we try to use systems in their linear operating range, all right. It is not always easy to do so, and we will see a procedure of how to linearize a nonlinear system in the so called linear operating ranges, all right, and that is essentially the topic of today's talk. Now, why we want to do this is primarily because of this reason. The analysis and control of nonlinear systems is very painful. It can get extremely mathematical, the computational effort is very high, and so on. On the counter, if you look at the linear approaches, you have excellent simulation design tools, you have simulation packages, so on and so forth, primarily relying on linear algebraic approaches, all right. So, the only option we have, because all systems are nonlinear, the only approach we have is to linearize the nonlinear system, okay, and we will explain how we are going to do that. We need 3 concepts. The first is the concept of equilibrium point, the second is the concept of the Taylor series, and the related notion of the Jacobian. Using these 3, we will show you one specific way of linearizing a nonlinear system, okay. So, now that we know that this is what we are going to do, linearize the nonlinear system. So, first let us look at the general expression for the nonlinear system. So, if you recall, linear state space system was x dot equal to ax plus bu, y equal to cx plus du. Let us ignore the inputs and outputs for the minute. So, what we will have is basically a system of the type x dot equal to a times x, all right, and notice that a is independent of x. That is the crucial thing. A may be a function of time, A may be constants, whatever it is, but it is independent of x. In the nonlinear system, you have the classical way of denoting a nonlinear system dynamics as x dot equal to f of x, okay, and f of x comma t is specifically a nonlinear function of the states x of t, okay. Of course, in the linear case, f of x would just be equal to a. Now, I can write my dynamics as simple example would be say 3x square, all right. or I could write x dot equal to sin x times cosine of x. These are all examples of nonlinear system, and we essentially are just calling these as f of x. Okay. So, that is a general notation for a nonlinear system. Now, it is very important to understand the concept of an equilibrium point, and the definition of an equilibrium point is as follows. So, given a nonlinear system x dot equal to f of x, as we have seen before, a point x, or we can call it as x naught, some people also use x star as another notation. A point x naught is said to be an equilibrium point of this nonlinear system x dot equal to f x if and only if at that particular value of x naught the dynamics is equal to 0. So, this basically means that x dot is equal to 0 when evaluated at x naught. Okay. So, that is the notion of an equilibrium point. It basically says at that specific point x in x naught in this particular case, your dynamics are 0. Okay. Let us look at one simple example of the so called scalar case. Remember that when you talk of states, you have state vectors. So, in general we would talk about x as actually being a vector of states, right. For this particular slide, let us ignore that. What we are going to really look here is just a single state. All right. So, let us look at this example of the RC circuit, and we can write based on the Kirchhoff's voltage law this relationship over here, where the voltage across the capacitor plus the voltage drop across the resistor, it basically sums up to 0. All right. So, when I rewrite this expression, I get dV by dt plus V by RC equal to 0. Now, what is the equilibrium point for this particular system? That is the question. And the procedure to compute the equilibrium point is really straightforward. We know that the definition says the derivative must go to 0 at that particular point. Okay. Now, what we are going to do is to write dV by dt equals minus V by RC. All right. To compute the equilibrium point, I need to set this to 0. Now, this is equal to 0 only when V is equal to 0, right, because no one will take R or C equal to 0 and construct a circuit like that. So, R and C will be non-zero values, and this equation holds true only when the voltage across the capacitor is equal to 0. All right. So, this is an equilibrium point. Now, there is actually an interesting equilibrium point, and we will come to one of this notion a little bit later in a more complex case. So, first of all, remember we computed and said that when the voltage is equal to 0 for this model of the system dV by dt plus V by RC is equal to 0, this is an equilibrium point, okay, because the dynamics is actually equal to 0. Now, the solution of this simple first order differential equation is basically this one. So, V naught e power minus t by RC, okay, where RC is your time constant basically. So, now the question is, we know that when V is equal to 0, all right. So, when you start the circuit simulation with the initial condition such that V at time 0 is equal to 0, all right. In this case, for all future time, this answer will be 0, all right. It will never be a non-zero value, it will always be 0. Now, what happens when we start at a different initial condition, say for example, V of 0 equal to, it could be 5 volts, all right. We see here that V of t will be equal to 5 e power minus t by RC, and for any reasonable say combination of R and C, as t tends to infinity, actually it does not even need that much time, but as t tends to a sufficiently large value, V of t will tend to 0. So, what this means is that when my initial condition is 0, the dynamics of the system will always stay at 0, it never goes to any other finite value. When I start at any other initial condition, my dynamics will always converge to 0, all right. So, if I actually draw x and t as a function of time, actually v, sorry about that. So, if I take v as a function of time, if you start over here, okay, at the origin, initial condition is equal to 0, you will never have dynamics going anywhere else, it will always stay there. You can start anywhere else over here. This can be an initial condition, this can be an initial condition, this, whatever it be. You will always converge to this value 0. Okay. And it turns out that this is a specific case of what is called a stable equilibrium point, and more specifically a globally stable equilibrium point. Now, we will not go too much into these definitions, but when you look at design and analysis of control system, these concepts become very clear. Okay. So, let me summarize this slide, basically saying that a particular point of your solution, we are looking at V over here, one of those values of V is said to be an equilibrium point if the dynamics is always equal to 0 at that particular point. And we also have a simple procedure to calculate what that equilibrium point is, which is basically you equate the derivative to 0 and you solve for that f of x, and that is what you get. Okay. So, this is basically what I said in the previous slide, that if you start off your dynamics, let us say if you start your dynamics at x naught, where x naught is your equilibrium point, okay, the dynamics will always remain at that particular value for all future time t. It also means that if I start at any other initial condition, okay, and accidentally or through design or whatever, the system manages to reach that particular state, from that time onwards the system will be essentially stuck at that state forever, all right. So, that is a basic notion of an equilibrium point. And of course, there are various kinds of equilibria, there are saddle points, centers, all kinds of things. We will encounter one or two of them in this particular lecture, otherwise it is actually a fascinating study. Okay. Now, we have been talking about equilibrium points, we have been talking about linearization. Now, there is a natural question which comes, why do we want to linearize about an equilibrium point, why not somewhere else? The answer to that is fairly, one is a very practical reason, and it is basically that it is very easy to compute the solution of differential equations at the equilibrium point. All you need to do, as we have seen in the previous slide, just equate the derivative to 0 and just solve it. Generally, it is fairly straightforward, as opposed to computing the general solution of the differential equation itself, which can be very complex. The second and more relevant reason, more important reason, is that we have theorems which actually guarantee that if you linearize a system about in the neighborhood of this equilibrium point, right. So, if you linearize the system at this equilibrium point, we are guaranteed that the behavior of the system at this equilibrium point is very similar to the behavior of the system anywhere else around the equilibrium point in a small neighborhood, right. So, in the previous case, we had the RC example, and we saw that the value of 0 is an equilibrium point. You start anywhere close to 0, right, say 0.0001 or whatever it be, in a very small region around that equilibrium point, your behavior will be very similar to what it is at the equilibrium point. Okay. Fine. So, that is basically why we look at linearizing around an equilibrium point. Okay. So, let us actually first look at a slightly graphical sketch of how we would approach the problem of linearization, and in the next slide we will actually see the so called Taylor series and a more formal way of doing the linearization. Okay. All right. Let us say that we have this parabolic like function in the blue line which we are seeing over here, and we want to actually fit another function to this one, all right, and or rather we want to approximate this function, and there is various ways of approximating such functions. So, in the first case I can simply have that at a okay, so let me call this as x and let me call this as f of x. Okay, x is an independent variable and f of x is a function. Okay. So, as x varies we have a change in f of x also. Let us take a particular value of x, say that we take x equal to 0 at this point, okay, and then we compute what is this f of 0. We will get some value, let us say it looks to be about say almost 1. Okay. Now, this is one approximation to this curve, right. So, you have this curve and one particular approximation to this curve says that I know this particular value. I do not know the rest of the curve, but I know that one particular value. Well, that is a good start. Now, what can we do once we know this one particular value? Well, we can actually compute the slope, right. This looks like a nice curve, and one of the nice things we can do is just compute the slope over here, all right. The slope, so if this function is f of x, the slope over here would simply be partial f with respect to x, all right. Now, this is another approximation. So, the way I would actually write this is, let us take this particular value in x, we will call it as a. So, x is equal to a. So, at the first instant I got the value of f when x is equal to a, we will call that as f of a, right. Now, to that I am going to add the slope over here, which is a straight line, right. So, I will add plus partial f by partial x, okay, and essentially I get this kind of this is an approximation now. So, all I am saying is, given my nice parabola, I now have an approximation to the parabola which is a straight line. Clearly, this is not true, right. I mean, you still have all this deviation over here which needs to be taken care of. So, what we could do is now to fit this in a slightly different way. So, you had your parabola again and you computed this point, you computed a straight line. Why do not we actually try to fit a second order say polynomial around this particular point, right. Let us say that we are able to fit something like this. This is another approximation. So, what I am going to do now is to add a second order term over here, and when I add up all these terms together, the final fit to this particular curve will be something like this, almost what we want. So, this is a very good approximation of this particular parabola. Now, in general you may not have just parabolas, you may have say fairly high order curves, okay, in which case I may need to take first is my constant value, then I need to take a straight line, I may need to take a second order polynomial, need to take a third order polynomial, so on and so forth. All these curves which you are trying to fit to this particular polynomial are basically approximating this polynomial, right. So, this actually goes by the name of the Taylor series, okay. And the basic idea of this slide is that linearization is basically an approximation of a nonlinear function. How we do it formally is by the Taylor series expansion, okay. And so, we have already seen what this thing is, right. So, if I go back to the previous slide, you can see the animation over here. It is a second order, it is a third order, fourth order and so on, right. I can show this again. So, there you go, first order, second order, third order and so on, right. So, these are different fits to the particular function, and the way we compute those fits to the function is by using the notions of derivatives. We have already seen the first order derivative where we took the slope of the line, that is the slope of the line over here, right, slope of the curve, sorry. So, if we add up all these terms of the Taylor series, essentially you are actually going to have a perfect fit to your parabola, all right, and that is basically approximating the nonlinear function. And of course, where we approximate is important. We have already seen that it is better to approximate at the equilibrium point because it is easy to compute the solutions and other reasons, right. So, we always try to approximate at the equilibrium point. So, if you look at these terms over here, the f dash a, f double dash a and so on, these are nothing but the partial derivatives with respect to the independent variable. In this case, we have only one independent variable evaluated at the equilibrium point, right. F double dash will be the second order partial derivative evaluated at the equilibrium point, and so on, right. So, all the derivatives we are considering are with respect to the independent variable x, in this case 1, but in general it will be a multi-dimensional independent variable, right, because remember that we had the state vector which was x1, x2, so on till xn. Okay. So, let us see how that works out. Okay. So, in the previous case we had a function of the type, for example, it could have been x dot equal to 3x square, right, a scalar dynamics which you can call. Now, what we are going to look at is functions of two variables. In the next slide we will go to n variables and see how we can generalize this. So, when you look at functions of two variables, this can actually look as follows. So, x dot equal to f of x1 comma x2, right, and the way I can write this down as one specific example, it could be something like 3 x1 times x2, x2 dot equal to x1 x2 square, right, something like that. Now, this would be my f1 of x1 comma x2, this would be nothing but f2 of x1 comma x2, right. That is basically this expression expanded in two equations. Okay. So, that is basically what we are saying. If you have a state vector with two states and the dynamics of state 1 depend on state 2 and vice versa, this is captured in the two dimensional function f of x1 comma x2, okay, and that is exactly what we have done over here. So, this is a two dimensional state space system and we have two functions f1 comma f2. Remember, in the previous case when we had the dynamics like this x and f of x, right, with this parabolic thing, say I don't know x square or whatever it is. So, when we had this kind of an equation, we actually considered at the equilibrium point, in this case equilibrium point is over here. So, we considered at the equilibrium point the derivative of f with respect to x, right. So, basically we are trying to understand how the dynamics of the system changes with respect to the independent variable. In this case we had only one independent variable. In our example, in the current example we now have two independent variables, right. So, if we try to look at it visually, it will actually look something like this. So, I have got a x1, one of the independent variables, the other independent variable is x2, right. Then you have your function itself f of x. So, for a change in x1 and a change in x2, I will have a particular value of f of x, right. So, typically this would be a surface or something like that, right. So, now because f of x which is basically x1 and x2, because f changes with respect to x1 and x2, I need to compute two derivatives. Okay. So, one derivative will be with respect to x1, the change of the dynamics in the x1 direction, the other derivative will be the change of dynamics in the x2 direction. Okay. Now, we need two derivatives, unlike in the scalar case where we just use a single derivative, all right. Okay. So, how will that look like? Well, if you just write the Taylor series and you ignore the higher derivative terms, we can call it the higher order terms. Okay. So, we take only the first order terms over here. For the first equation x1 dot or the first state in our case, we actually have these two expressions over here, right, the derivative with respect to x1, the derivative with respect to x2. These are, again I am repeating, they simply are capturing the change or the variation of your dynamics, your system in the x1 direction. This one is capturing the variation of the dynamics in the x2 direction, which is why we always have two derivatives. Similarly, f2 also varies as a function of x1 and x2. So, again you have these two derivatives. If we put these derivatives in a matrix form, you have this kind of a structure over here. Okay. It is a square matrix again, and essentially you are going to just take all the partial derivatives and then put it over here. Okay. Now, this is a special kind of a matrix called the Jacobian. and the Jacobian basically is derived from the Taylor series, right, the first order terms of the Taylor series. We are ignoring the higher order terms, because in general first order terms are usually good enough approximations to the nonlinear functions, in general, not always. Okay. Now, we know how to handle second order dynamics. How would we handle nth order state space system? Well, based on what we have just seen, for a second order state space system, if we compute the derivative with respect to x 1 and the derivative with respect to x 2, for a nth order you will just keep on going until you compute the derivative with respect to x n. All right. Now, note that when I say f, it is not just f, it is f 1 and so on. I will have f 2. Okay. So, the derivative of f 2 with respect to x 1, so until derivative of f 2 with respect to x n and so on. Put all of this in a matrix form, and this will essentially generalize to this kind of a structure. Okay. So, this is your the classical, the Jacobian matrix, and this is where we stop one part of the lecture. And what we have done so far is the following. So, we have a nonlinear system, or we have the dynamics of the nonlinear system. Okay. We have then computed the equilibrium points. We have defined it and just said how we can compute the equilibrium points of the dynamic system. Okay. And finally, we have seen that to approximate the nonlinear function, we actually use the Taylor series, and as far as possible we typically use only the first order derivatives of the Taylor series, right. So, we use a Taylor series, the first order derivatives, and then we compute the Jacobian. Okay. So, this is what we have done so far. Now, the question is, how do we go from the Jacobian to the linearized state space system? How do we get the linearized state space system once we have the Jacobian? And by the way, I will be deriving one or two examples for the Jacobian. So, this will become clear in a couple of slides. Okay. So, how we go from the Jacobian to the linearized state space system is as follows. So, again, all of this is at a high level. When you look at the example, it becomes much more clear. So, first we have computed the equilibrium point, which we have talked about, and then we compute the Jacobian. So, I would actually include another point over here. I would say compute the Jacobian, right. So, first we compute the equilibrium points of the system, then we write down the Jacobian, the matrix basically, and the equilibrium points which we have, we substitute the equilibrium points, okay, into the Jacobian, and we will see an example of how to do that. When you substitute the equilibrium points into the Jacobian, what you are going to get is a linear A matrix, okay, and that is it. It is as straightforward as that. So, the procedure is you write down the nonlinear state space equations, compute the Jacobian, compute the equilibrium points, substitute the equilibrium points into the Jacobian, and this gives you the A matrix. Okay. A point which we will come back to maybe in the next slide, which is very important, is that the computed linear A matrix or the system matrix A is valid only at the equilibrium point and in a small neighborhood around the equilibrium point. It is not valid anywhere else. Okay. We will see that very shortly. Okay. So, if you rewrite this a little bit, so we have the basic nonlinear dynamics, then we compute the equilibrium point, the Jacobian, and you get x dot equal to Ax, and this is the linearized model of x dot equal to f of x. All right. So, there we go. Now, yeah, okay. So, one example is if you take the Tejas, our Indian light combat aircraft, or for any aircraft for the matter of fact, and aircraft, the general nonlinear dynamics are very complex, right, and you really can't design simple controllers for these really nonlinear dynamics. So, what engineers have done over the past I don't know 50 years or so, they have designed what are called as linear models at each operating point of the aircraft flight path. Okay. Say for example, just one particular example, if we okay. So, this is the terrain earth, and the aircraft's trajectory basically takes it along this path. Okay. So, we have our wonderful Tejas, which is actually flying around this path. Now, at each and every point on the flight path, multiple changes happen. Okay. So, what are these changes? Let us actually write some of them down. So, your wind your conditions change, atmospheric conditions change, the pressure conditions change. Okay. Of course, when wind changes, even turbulence and other factors also change. So, your pressure changes, that these are the external parameters. The internal parameters are that the fuel is reduced a little bit, your plane may be having some extra drag because of the kind of wind conditions which are affecting it, and so on, right. Each of these changes, every single change actually changes the model of the aircraft dramatically. So, these are actually called operating points, right. So, as we go from one operating point to another operating point, the model of the system is actually different. So, what people have actually done is to take each of these operating points, okay, and linearize the system around this operating point. Okay. So, to get a matrix, take another operating point and then linearize it over there, and so on and so forth. So, now you have a bunch of system matrices A1 to AN along the flight path of the aircraft. For each of these system matrices, each of these matrices, they actually design a controller. Okay. So, corresponding to each matrix, you now have a controller. So, I can call this K1, I can call this K2, so on until Kn. And this is in flight control literature, this is actually called as gain scheduling. Okay. So, without getting deviated from our topic, the idea of this example is that this is a highly nonlinear problem, right. This flight path which encounters so many changes in wind, pressure, fuel, drag, lift, so on and so forth, is a very highly nonlinear system, and the only way we can handle it, at each operating point of this flight path, we actually linearize the system, right. So, then you get this set of linear models, and for each model we actually design controllers. Okay. So, this is how it is classically done in aircraft industry, in chemical process plants, and so on.